So let's have some paper out and go ahead and try this for a warm-up. A little proof that I mentioned we would do last week. So this will be the warm-up. This is what I want you to prove. It's the change of base technique with logarithms. So I want you to prove that the log base A of n is equivalent to the log base b of n all over log base b of a. So that's a formula or a technique that is allowing you to change from base A to base B. Let's make a note of that down below. So this allows us to change from one base to another. So this changes from base A to base B. So that's base A, not base A. From base A to base B. So that's base B, not base B. Alright, that's what it does. And here's a hint. And remember, for proofs, you've got to pick the left side, log base A of n, and only do math that you understand and you feel is accurate to create the left side to become the right-hand side. Kind of like proving trig identities. And here's your hint. Try this. Use y, just another variable to pick to do some math with, equal to log base A of n. So let y equal log base A of n, and then try to rewrite that based on what you know about logarithms and exponentials, and go back to the original problem and see if you can create log base A of n is the same as log base B of n over log base B of A. Alright, give it a shot. Pause the video and then come back to it. Alright, hopefully the video was paused. Hopefully you worked on it for about 5 or 10 minutes. If somebody in class thinks they can share it, great. Otherwise, here's a technique that you could use to go through and show that. If we use the hint that y equals log base A of n, we can take that and we can rewrite that. So from that hint, we can say that A to the y power equals n. So we can do that to the original value of y equal to log base A of n. And now we can take the logarithm of both sides of that equation, and we're going to take the logarithm in terms of base b. So take the log base b of the left-hand side and log base b of the right-hand side. And because logarithms represent an exponent, and that y variable is like having an exponent on an exponent, we can rewrite that as y times log base b of a equal to log base b of n. Now remember, we defined y to be log base a of n, which is just what we're trying to prove or rewrite into the log base b of n over log base b of a. So now you probably can see, if you think ahead, where is this going to be taking us? So now that we have y times log base b of a equal to log base b of n, I can divide both sides by log base b of a, and now y equals log base b of n all over log base b of a. And you might be thinking that doesn't really prove anything yet, but it does, because we defined y as log base a of n. So if we go back and substitute what y was defined as, now we're showing that log base a of n is equivalent to a new base called b, and it's log base b of n all over log base b of a. And we did a problem like this in class last week when we were talking about rewriting problems in different bases. We had 81 and 3 and writing with different powers of x, and changing the bases was called the basis for disguise. We also did 5 and 7. So as an example, somebody did this. Somebody wrote a problem, and they wrote this. They wrote, I think it was 5 to the x equals 7, and they wrote that as log base 5 of 7, and that was a logarithm. And somebody else in class also wrote it this way. They went to base 10, and base 10 is log with no number, so it's assumed to be a 10. They wrote that as log of 7 over log of 5. So that's how you can use change of base. Log base 5 of 7 can't be computed in most calculators, but if you go to base 10, which is log, L-O-G, that's equivalent to log of 7 over log of 5. So I change that from base 5 to base 10. Okay? All right, so that's a proof of how you can do change of base formula with logarithms. All right, so this is what we're going to look at today. Let's call it differentiation, old and new. So it's a differentiation. We'll look at some old work, some new work, and hopefully see why we need another technique and than what we've seen so far. So differentiation, old versus new. So let's call the first part, part 1, we'll just call it this. We'll call it the old. And by the old I mean this, functions we can differentiate. So we'll call this functions we can differentiate. And we'll just take a few minutes just to remind ourselves, oh yeah, these are problems we can do. So functions we can differentiate. Just as examples. We did these functions quite a while ago. We looked at problems like y equals 5x. And that was pretty straightforward. That has a slope of 5. The derivative was 5. We made that connection. We also looked at power rule functions. So we had something like f of x equals 6x to the third power, where you can bring that power down and use power rule. We also looked at functions that were a little more complicated. We looked at functions that were products. So you could have a product and you didn't have to go through and multiply it out, but you could do something like x to the 5th power times the quantity 3x minus 4. So that's a function that we can differentiate. So we had different properties and different rules we looked at. We had product rule, quotient rule, power rule, and other traits of derivatives, but that's the old work. And it wasn't too complicated once we got the hang of it, and it really was using power rule with some adjustments. What we'll look at today that's different is things that we can take the derivative of using just those techniques because they're a little more complicated. So we're going to call those the new, and we'll look at a couple of them. We'll do some practice problems, and then you'll have some of these for homework. So we'll call this the new. These are functions we cannot differentiate. So we'll call these functions we cannot differentiate. And we'll just look at them first, and then we'll talk about why not and how do we do this. So functions we cannot differentiate, and we'll look at a couple of examples. So here are some functions that we cannot differentiate. Let's look at 3 problems. First one, y equals the square root of x squared minus 4x plus 5. So all of that is under the square root. So it's not a power rule, and we can't write that as a power of x because that 1/2 as an exponent from the square root doesn't, in a sense, distribute over those 3 terms. So there's no way to simplify that square root. It's not a power rule, not a product, not a quotient. We're kind of stuck with it. A different example that we cannot differentiate, or at least I don't want to, would be if I gave you f of x equals the quantity 2x squared plus 1 to the 5th power. That we could multiply that out and multiply 5 of those 2x squared plus 1's together and simplify it, and the derivative of that's a lot of work. There's got to be a simpler way. Another one we can't take the derivative of is this. F of x equals the quantity of 4 over 3x minus 2, and all of that to the 1/2 power. So yeah, that's like the square root, but that fraction doesn't simplify. The top could be simplified, the bottom can't be simplified. So we have a quotient, but it's not purely a quotient rule because of the power of 1/2. So something has to happen to that power of 1/2 that we got to deal with that. All right, so we'll look at how to figure these out. And the method we're going to use is called the chain rule. So we'll put a star by that. We'll call this the new method. And we'll look at a couple of these examples, and we'll go from there. So this new method is called the chain rule. And, lots of other examples of this online if you want to look things up. But the chain rule allows us to work with a little more complicated problems that are actually a composition of 2 other functions. So chain rule says this. It says that if you have a composition of functions, so they use this notation. They call this function, as far as the definition, they call it f of u. And when they say f of u, they're not trying to be funny. They really mean that we have a composition of functions. So it's a more complicated function than simply f of x. So f of u really represents a composition of functions like f of g of x. So there's a function within a function. So you have something fairly simple, but because there's more math done to that simple part, it becomes a composition. So they use that notation. F of u really means like f of g of x. So there's something that's fairly involved within another function. And the derivative of that is the following. And there's a proof. There's proofs online. There's proofs in the book. They're fairly involved if you care to look at that. But here's how you find the derivative of a function that is a little more complicated than your typical function. So d dx of f of u is the following. You take the derivative of the original function, so as it is, whatever function it is, and you multiply that by the derivative of the u part, and we'll talk about what the u part is in that problem. So it's like taking the derivative of the whole thing like you normally would. It's kind of like one big power rule problem sometimes, but there's also an additional factor, that u prime, that derivative of u, that you have to add on. So sometimes written this way. Sometimes if we're just talking about powers, you can think of it this way. So it's also like saying this. You have d dx of some amount raised to the n power. Now notice that's u to the n, not x to the n. A power of x would simply be power rule, but this is u to the n. So the derivative of that is n comes down as a multiplier like we've seen with power rule. And then we have that u amount, and we still decrease the power by 1 times, so it's to the n minus 1 power. But the additional multiplier is that u prime. So that's the big difference both times. You have that u prime multiplier. Okay, so let's look at an example of that. And remember, this is a video, so if you want to stop the video and go through and look at some things, or you're not quite caught up, or this wasn't clear, or you just got back from using the restroom and you missed something, the substitute can rewind the video, and or you can watch it tonight at home and make some popcorn and maybe share a moment with your parents. So let's look at that problem and look at a couple examples of this, and then we'll see how much more we want to do. So let's go back to the first problem that I gave you. Here's an example. Here's a function of the type that we said, hey, we can't find the derivative of this. So we have the square root of x squared plus 4x, or minus 4x plus 5. Okay, so that's a composition. It's really simply x squared minus 4x plus 5 composed with the square root of x. So you have the square root of x is the basic idea, but you also have the x squared minus 4x plus 5. And you've got to deal with that. So let's look at it actually Two different ways. One way is this. Now we'll call this using what's considered U substitution. And this is a pretty efficient technique that you'll see in quite a few problems because it lets you make the problem a little bit more simple, and it kind of gives you some direction of how do we approach it. And it's very common in math to take a complicated part and call it a single variable and work with that. So this is called U substitution because we're going to use the letter U. So go to this problem and do this. Let's define U as the part that is under the square root, because then we actually have a simpler looking function. So now instead of y equals the square root of x squared minus 4x plus 5, we have simply y equals the square root of u. And as a power, square root of u is u to the 1/2. So now my derivative of that original function, so this is that ddx of u, or f of u, is the following. So my derivative now, or my y prime, is the derivative of u to the 1/2, but there's two parts to that. It's like a power rule, where you take the 1/2 times u, and you decrease the power by 1 whole, so that's negative 1/2. But what's different with chain rule is that because u wasn't simply a power of x, we must multiply by the derivative of what u was defined as. So by using u equals x squared minus 4x plus 5, u prime, the derivative of that was 2x minus 4. So that's an additional multiplier we must include in this problem. So that's our u prime. Now we use u as a substitution amount to make the math a little bit simpler. So to finish the problem, we have to go back and say, all right, let's rewrite everything back in terms of x, because that's what we were given in the beginning. The u substitution was just supposed to make it look a little bit simpler. So here's everything put back in the original variables. And then we'll just go through and simplify that. So that's the derivative of the original function, and I'll show it using just like a variation of the power rule too. So two things are going to happen. To make this negative exponent a positive exponent, that's going to go under the fraction bar. This will be above the fraction bar. So I have 2x minus 4 here, and then my denominator is going to be a 2, and then I have x squared minus 4x plus 5, and that's to the positive 1/2. And then I could do one more little bit of simplifying. I could factor a 2 from the numerator, from the 2x and the 4, and cross that out with the common factor of 2 in the denominator. So I'm going to get x minus 2 on top, and the bottom becomes x squared minus 4x plus 5. All of that to the 1/2 power. So that's my y prime, or my f prime of x, or my ddx of f of u. So that's the derivative. So that's using u substitution. The other technique that I showed you, that n, u to the n power, is this. So you can also think of it as this. So if you don't do any u substitution, you can also think of it as, well, here's my function, and I have not a power of x, but I have a power of x squared minus 4x plus 5. So I still treat that as power rule, but what chain rule and the proof using composition shows is that it's not as simple as, well, just go through and do power rule and be done. There's two things involved. You still bring down the exponent as a multiplier. You still decrease the exponent by 1 whole, and that becomes a negative 1/2. But there's that additional multiplication factor you need, which is the derivative of what was raised to the power. In this case, it was that 2x minus 4. Okay, and that in the end is going to be that same answer. So chain rule requires an adjustment because we don't simply have a power of x, we have a power of a more complicated expression. Okay, let's look at one more. Remember, this is a video. You can stop it, rewind it, make some popcorn. You've got that option. All right, one more. Second problem that I gave you, that was a problem that I don't want to find the derivative of the way it's written. So f of x equals the quantity of 2x squared plus 1 to the 5th power. and I don't want to multiply that out. That's going to be a lot of work, so I can treat my u amount as simply the amount raised to the power of 5. So here's my chain rule derivative of this problem. I treat it like power rule. The 5 comes down as a multiplier. I decrease the exponent by 1. But chain rule requires one more thing. Multiply by the derivative of what was raised to the power in the first place. And the derivative of 2x squared plus 1 is 4x. So there's my final answer. 5 times 2x squared plus 1 to the 4th times 4x. If I simplify that, I get 20x times the quantity 2x squared plus 1 to the 4th. And that's it. So that's the same answer you would get multiplied it out, but it's a whole lot simpler not to take 5 of those 2x squared plus 1s and multiply it. And that's a derivative. So the substitute will show you a couple of examples to try on the document camera, and then they'll show you the answers, and I'll work them out for you. And then your homework is on the calendar. Good luck. I will see you soon. Bye.